Welcome to a talk on cross-cloud app splitting with WebAssembly. I am excited about this because it's a very new technology, little on the peculiar side, and so you're going to get a look at something kind of exciting, I think, that we've been working on for a while. I'm Matt Butcher. I'm the CEO of Fermyon. I'm feeling kind of nostalgic today, so I'm probably going to end up telling a lot of stories just because it's kind of where I'm at. I live here in Colorado. Big fan of open source summits. Have been to many, many of these over the decades, at KubeCons as well. I really, early in my career, did a lot of content management stuff. And I've had sort of like a very serendipitous career where I just feel like I keep landing in interesting places at the right time. And had been at HP doing content management work right when they started the HP Cloud project. And HP Cloud was built on OpenStack. I ended up sort of migrating from CMS into the cloud world early on. HP Cloud never really took off, but my interest in cloud really took root. And I ended up sort of going from technology to technology there. And that has really become sort of the foundation of my technological interest. So I'll touch on that quite a bit today. But even before that, I've been an application developer for the vast majority of my career. Early on, the pattern that I grew up using as a Java developer was what we now call sort of monolithic server systems. Of course, as cloud emerged and then cloud native emerged, microservices became a much more popular way of building things. So let's really quickly just define those two terms so that we understand them. A monolith is a system where the entire application is one giant code base that is deployed in unison, pretty much runs as one single binary, one single runtime. Microservices, in contrast, are broken down into pieces. So you take the application as a whole, you break it down into constituent parts, and they usually talk to each other over, say, HTTP or message buses, and you can basically componentize different pieces of your architecture. Each of them has some pros and cons, and we're going to talk about the pros and cons of each. But really, the thing I want you to keep in the back of your mind is, hey, is there a way to kind of get the benefits of both without some of the real drawbacks of each? So monoliths. Way back in the early days of the web, I worked at a company called WebMD. It was one of my first jobs. And we built the quintessential monolith. The architect, Lee Boynton, was actually one of the creators of the Java programming language, so he knew it through and through. We built an application that started with the socket API. We had our own custom HTTP server we built on top of it. On top of that, we had what we would now call a message bus, but a sort of message passing system built in. On top of that was a repository system like most modern CMSs have. On top of that was a data, sort of like a pipeline system that would allow us to set things to run in sequences and run through a data processing sequence. On top of that was sort of the content access and address mapping layer, and on top of that was a template engine. This thing was all one giant application, from the HTTP implementation all the way to the template renderer. And we had 50, 100, 150 developers all working on this one code base. It had some real advantages. It was a very, very cool system. But when it came to deployment, it was very difficult to deploy. I think the longest working day of my career was 36-ish hours. When we started a deployment at midnight, it went sideways, and because all the developers had contributed to the thing that was being deployed, we all had to stay online for the entirety of the deployment until we got the whole thing out. And it was a marathon, to say the least. I'm glad I've only done it once in my career. But so they were right there. You can kind of get some hints of the pros and cons of a monolithic system. We'll come back to that a little bit. Fast forward into sort of the cloud native ecosystem, right? I was one of the people who early in the Kubernetes, the life cycle was chanting very loudly, microservices are going to destroy monoliths. They have all these great advantages to them. The Go programming language turned out to be a great language for building microservices. Worked in Kubernetes a lot and would build these sort of systems that were decomposed into constituent parts. One of the ones I was most excited about was I worked for a little while at Nest Labs inside of Google. And we built a very microservice-oriented architecture. But one of the drawbacks to the microservice architecture in that context was that we had so many services that I, as a developer, couldn't really run any semblance of the whole system on my developer workstation. In fact, I could really only run sort of a subset of it, and of that subset, most of it was mocks, and I really only had a couple of actual services there. It worked most of the time until something in the mocking layer didn't quite behave the way something in production behaved, or until one of the services I was not running locally did something that I didn't expect when I was writing code. And so I have sort of, I tell these two stories to kind of frame out two pieces of reference, and I'll touch on them as I come back and forth through the talk, right? There were pros and cons of the monolithic architecture, pros and cons of the microservice architecture, and they just kind of surface in different ways. But let's actually enumerate what is sort of behind some of those problems that I was talking about, right? So monolith, right? Think the WebMD application, this big giant, HTTP to template render all in one code base. That was good. When it came to onboarding a new developer, they needed one repository to access, right? When it came to looking at the code, you really had all the code right there. You could inspect anything. That actually, skipping to that third one, made debugging a lot easier. Because when something went wrong down here, and all I knew was that when I did this way up here at the top of the stack, something bad happened way down here, I could actually trace all the way through. Since switching to microservices, by the way, I don't think I have set up a debugger in years because I've found them to be so much less useful. But in the monolithic app world, there was a sort of comfort to be derived from the fact that I could set a breakpoint here and a breakpoint here, and then sort of, bisect my way down into whatever the actual cause of the problem was. The other nice thing about the monolithic development from the point of view of a developer was that it was relatively straightforward for me to set up local development, right? Everything was there. I check it out, I run one build command, the whole thing is running, and I know with confidence that the thing that I am looking at is representative for most important reasons of what would be running in production. But there were some, serious drawbacks to the monolithic environment, and those were ultimately the reason why we started doing more microservice development, right? Internal complexity is high, and that WebMD example is a perfect illustration of this point, right? Why would I, when I'm working on a template, be working the same code base that had the TCP muxing algorithms for HTTP, right? I could at any point start looking at pieces of the code that I had no idea how they functioned, why they were there, anything like that. And we were all working on the same code base, which meant code reviewing was a little bit hard. Different people were trying to find the right people to review this chunk of code. Sometimes these massive PRs would drop that were like changing. We didn't call them PRs back then. We were using CVS. These massive changes would happen that would change things all the way across all these different layers, and it would be a bear to try and figure out how do I review this particular change set, right? Deployment, as I already hinted, that was a big one for us, right? When you're deploying one giant code base that does everything, in a sense, you have to have everybody sort of available when something goes wrong. So deployments were tremendously stressful because the whole development team was on standby, because you never knew which piece was going to break when it deployed, and if it broke, you better be on the call because otherwise you'd get yelled at. But deployment really in general was hard because since state was tracked inside of, and this is typical of monolithic applications, state is tracked inside of the application, it's not easy to sort of do the typical blue-green deployments and some of the other strategies we often use now that we have microservices. Over time, the code base got more and more difficult to manage, and I think this is true of pretty much all the monoliths I've worked on. They start like this big, they grow to be this big, they grow to be this big, and before long, the code sprawl is so huge, and everybody's afraid to touch anything that you start to have these sort of swaths of legacy code, in strata inside of your application that nobody wants to tinker with because it's the boundary between these 3 experts here and these 5 experts here, but nobody wants to mess with the middle layer, or because this guy who wrote the TCP stuff is now gone and nobody wants to touch that layer of code. And you end up with sort of like this accreted unit of code that becomes difficult to sort of cope with. And the result of it was it just kept getting bigger and bigger and bigger. Scaling was hard too, mainly because we at that point in time, and really I think it's true of most monoliths today, we talk about scaling vertically instead of scaling horizontally. Instead of starting up more instances of our app, which I think maxed out at 3 at WebMD, at New York Times where I did another one, we maxed out at something like 8. You just couldn't scale out beyond that number of instances of it before you ended up with problems because of the assumptions the system was making. So instead, we would scale vertically by just adding more CPU, more memory, more network cards until we could basically run this thing the way it needed to be run. That was expensive, and of course we hit limits, and once you hit limits, you can't put any more RAM in here, then you have to start making difficult decisions about what you're going to do with your code when it requires more RAM than you can run in production, for example. So a lot of those problems, which I experienced sort of acutely, were the reasons why I was so enthusiastic about microservices when that as a pattern began to take off. One feature of microservices I really liked and still do is the fact that because you assume that they will come online and drop off, because you assume that the same microservice will run in parallel, state is usually tracked outside of the application in a data store of some sort. So consequently, scaling got a lot easier, right? We could horizontally scale very easily. But from the developer point of view, because we had broken the complex into discrete parts, I, as a developer, maybe working with just a few other developers, could own a chunk of code sort of in isolation and be sure that we understood from line 1 to line 5,000 or whatever, everything that was happening in our little microservice. And oftentimes, it meant that as a development team, we could be a lot more nimble, right? Because we understood our part of the application front to back, soup to nuts, right? The downside, though, I'll finish with the pros, right? And the lower complexity per service is actually an interesting one to focus on specifically, right? When you start doing microservices that way, you end up with becoming API developers, right? And you think hard about what the surface area is, what the operations are that your particular microservice should be able to handle, what's in scope and what's out of scope. And consequently, because of that, you tend to keep the complexity relatively reined in. And in most of the places I've worked that used microservices as a design pattern, there was sort of either a hard and fast rule or a sort of soft rule that once one component in one microservice seemed to be creeping outside of its initial scope, you'd sit down and say, okay, do we need to break this into 2, or do we need to stop doing whatever we're doing over here, right? And that was all part of the fact that not just the pattern, but also sort of the milieu around it, right? The way we did the development process favored simplicity over complexity. The cons, though, as I mentioned before, debugging and local developer experience were huge, right? I stopped using a debugger once I switched to the microservice pattern because you're dealing with something over here and something over here breaks. And a debugger isn't going to help you with the 3 network hops and 2 other microservices that are running in between that. And so instead, you start developing your debugging strategy in a different way, where it's sort of like, okay, well, how do I capture what this request was, and then how do I replay that against this service? And really, a sort of holistic strategy for debugging supplanted my use of a debugger. And I think that's, maybe not everybody gave up on debuggers as quickly as I did, but I think we've all had that experience of saying, I write code over here, and 3 microservices over, something breaks. I can't just keep looking at my code and saying, what's here, right? I have to sort of see how the data flows through these microservices in order to understand what's happening here before saying, oh, when I made a request here, I was assuming that this system would do this and transform the data this way and put it into this system over here. So the debugging experience just changed. Local developer experience also changed. I told the story about not even being able to run the full Nest suite of microservices on my development workstation. And that is a story I think many, many microservice developers, particularly in larger scale organizations, can commiserate with, right? That if we do it right, we're building small constituent parts. And whenever anything gets complex, we're splitting it into multiple constituent parts. And so over time, we start having more and more microservices. And then the more microservices we have, the bigger the developer experience problem is, because suddenly I have to pull n+1, n+2, n+10 code bases down, figure out how to compile all of those. Many of the places I've worked with microservices have been polyglot, so it wasn't necessarily the case that I could just have Node and be able to run everything, or just have Go and be able to run everything. Before long, I've got like a Scala compiler, a Rust compiler, a Go compiler, the whole, 2 versions of Node, all to be able to run the different microservices that I need to be able to write my own code. I guess I have this sort of strong feeling, this strong opinion, that you want to kind of keep the division between operations and development, right? That operations, platform engineering teams, DevOps teams, should be able to gain their expertise and develop their expertise in the art of running an application, or the art of running a data center, or the art of running a platform. And developers should be able to stay specialized in solving the business problems in code and being experts in their programming languages, experts in their APIs and things like that. But with the microservice pattern, and this really exploded with Kubernetes, we just sort of said, okay, well now you both have to be experts in everything, right? Hey, software developer, now you have to understand how network is flowing through, how network traffic is flowing through the Kubernetes cluster, because you have to build your services according to that, right? And you have to be able to describe your infrastructure this way and that. I'll actually come back to that one a little bit. It's a mixed blessing in some ways as a developer, because you feel very empowered sometimes to be able to architect things the way you want. But it causes all this friction with the operations team that's going, you really shouldn't have developed the application this way, because now when I deploy it, I have to deploy it this way, and that's different from everything else, and it's going to be fragile in these particular ways, and we're going to have to adapt in these, and it just causes more friction than it should. The other thing that's always kind of bothered me about microservices is that you end up with a high amount of boilerplate code, because every single one of your microservices has an HTTP server and some kind of framework and JSON encoders and decoders, or whatever you're using for your language. And you find yourself just sort of rewriting the same logic over and over again, sometimes even in different languages, to do exactly the same thing, all of which is just to make sure that your microservices can talk to each other. It feels like we ought to be able to dive straight into the business logic and say, yeah, I don't need any of that boilerplate, right? I know what I need to do. I know that all these systems work the same way. Here's the business logic. But oftentimes in practice, we end up just re-implementing the same thing over and over again. Then we have to keep it all synchronized across multiple microservices. Otherwise, we just end up frustrating ourselves when this one's on version 1 of the library and this one's on version 2 of the library. The last one, and again, this sort of goes back to my ops versus developer distinction. Security has definitely become the kind of thing that we as developers have to become hyper acutely aware of, because every single one of these microservices needs to be sure that it's only accepting connections from the right upstream services and not the wrong ones, right? Our attack surface diagrams used to be like, hey, here's my monolithic app. These are all the places the user can hit. All the rest of this is relatively secure. And now it's like, hey, these are all my web services. All of these are different attack surfaces, right? Every one of these HTTP listeners is a place where an attacker could potentially gain access. How do I make sure the authentication is strong enough? How do I make sure the token management strategy is correct? How do, and security suddenly becomes such a big deal that both developers and operations teams are overwhelmed. And again, it just causes friction between operations teams who are like, no, the best practices that we're trying to institute are these. And the developers who are going, yeah, but I just need to get this done fast, and I just need to do this kind of thing. And it can just end up raising the tension again and again. So there we've got kind of a quick back and forth, right? It was not quick. We had a back and forth between monoliths and microservices, and where each has some strengths, but where each have some weaknesses. And I left that question in the middle that was like, yeah, but is there sort of like a middle ground, right? Is it conceivable that there might be a way that we could have, one code base like we did with a monolith, but where the application could be split and run as microservices, where we could still have that kind of easy developer experience of checking out one thing, building it, being able to run the whole thing locally, but still be able to break it apart into separate pieces when we need to deploy, horizontally instead of just sticking with vertical deployment, right? Is there a way to pull off all those pros and then start to sort of like shove all the cons off to the side, or maybe eliminate them altogether? So that's kind of the big overarching narrative. To get where we're going, though, we do have to take one little detour into the platform perspective, because a lot of this is tied to the way that cloud has sort of evolved. So way back in the WebMD days when I was working on this big giant monolithic application, we were also deploying everything onto actual bare metal. So at this period of time, there's a one-to-one relationship between the hardware and the operating system. There was only one operating system on one piece of hardware. There was a sysadmin who, regulated everything that went onto that particular operating system. He did all the upgrades. He made sure all the tools were there. He made sure all the libraries were up to date. This one guy, was kind of holding the weight of Atlas on his shoulders, but on the flip side, we knew that there was somebody there who was an expert in the operating system. And that person would make sure that that monolithic application could run. Over time, I think that one person became a team of like 7, but they were all still experts. Along comes this technology that really shook up that particular pattern, and that was the virtual machine. Suddenly, the fundamental assumption we had made that there was a one-to-one relationship between the operating system and the piece of hardware was gone. Now we could have multiple operating systems running on top of one piece of hardware, or multiple operating systems on who knows how many pieces of hardware, right? I have no idea how many actual physical servers are in Azure or are in AWS. I don't ever have to know that, and yet I can still use virtual machines, to do as big or as small of a workload as I want. But a funny thing happened when the development lifecycle began to favor virtual machines. And maybe this didn't happen universally, but it happened everywhere I was working, where we stuck with the monolithic pattern, but suddenly I, as the developer, as one of the developers on the team, got stuck with the duty of being the virtual machine image person. And I had to build the virtual machine image. I am not a sysadmin. I do not know how to run Linux for much more than like grepping and CDing my way through the directory structure. Definitely don't know how to do low-level optimizations to the TCP/IP stack inside of Linux. And yet suddenly it was my responsibility to build the virtual machine image, and then I would hand that over to the operations team. And then there'd be a vulnerability in a library I didn't even know was running there, in a system I didn't intend to be running there, and it was my responsibility to fix that. And as a developer, I discovered that my responsibilities had broadened from writing code to also being, sort of a static sysadmin, a one-shot sysadmin who got to try and configure everything just right once and then shipped it over to somebody else who would tell me 3 months later whether I was doing it right or wrong. And that was not an ideal situation. But it still worked well for monolithic applications in that I could still control all the assumptions I needed to be able to deploy applications like this. Containers came along and made many developers, including me, enthusiastically happy, because suddenly I was responsible for, instead of the whole operating system image, 3 gig from kernel all the way up to my application, to just like this little pie-shaped slice of a file system plus just the things I needed plus my application. And not only that, they were really easy to build and they were fast and the binary sizes were relatively small. So as long as I was writing a long-running daemon process, like a server, then I could definitely wrap my hands around what I needed to be able to build a Docker file, or at least I thought so at that time. Along with Docker, because of Docker's sort of runtime preferences, with virtual machines, we assumed the virtual machine would be around for days, months, quarters. With containers, things kind of shifted. And I don't know whether, I mean, it would be interesting to sort of retroactively go back and meet past me and past other, Docker developers and people like that and go, did we shift because Docker was really that unstable that we really didn't think we could run things for a long time? Or did we actually design it such that the assumption would be a Docker container runs for hours, days, weeks, instead of days, weeks, months, right? But we started assuming that a Docker container was more or less ephemeral, that it would start up, it would run for a while, it might die, it might get replaced with another one, and that pushed us into really embracing the microservice design pattern, because suddenly we needed to track state externally of the Docker container. Suddenly we couldn't assume that the file system was going to have the most recent whatever that I had just written there, because it might have crashed and something else had started, right? So containers, first of all, solved some problems with the virtual machine world, but really kind of helped developers pivot off of the monolithic environment and onto microservice environments. At that point, while I was working on this kind of stuff, I was at Azure. Came in through an acquisition. Basically, we were early Kubernetes developers and got put into the Azure and said, hey, half of you are going to go build AKS, the Azure Kubernetes service. The other half, Matt, your team, is going to go build stuff that is related to containers, and you're going to open source it, and you're going to help Microsoft kind of repair its reputation for calling Linux a virus and all of that kind of stuff. And we had a great time, because effectively my team's job was to go out there and talk to people and say, so, how's this whole microservice container thing going? What's causing problems? What's working well? And then start building projects that addressed various pieces of this. So we built Helm, which is the package manager for Kubernetes. We built CNAB and OAM and all these different technologies that were all designed to sort of plug holes here and there. But anytime you're engaged in that kind of Swiss cheese filling experiment where you're like, oh, there's a hole, I'm going to go plug it. Here's a hole, I'm going to go plug it. You start coming up with holes that you don't have any idea how to plug. And at some point, we had quite a few of these. And they all sort of revolved around the same shortcomings with containers. First of all, I was still playing a little bit of the sysadmin role, right? Because when the base image went out of date, or when a library was, a security vulnerability was discovered in a library, suddenly it was my responsibility to go in there and rebuild. I remember one day at Microsoft, a particularly prominent SSL vulnerability hit, and we had something like 1,400 different containers to rebuild and then deploy in a day in order to patch all of those. And that's a huge burden. So you imagine 1,400 different microservices or services out there running. All those development teams had to stop what they were doing and go fix something else, and lost at least a day of work on their core projects in order to fix something that was essentially upgrading a library, right? So that experience, just living through that, made me go, oh, wait a minute. So I'm still playing this kind of sysadmin role, even though this is not what I'm good at, right? Containers are still pushing me into that environment. And even if you look around at the container ecosystem today, increasingly you're seeing a lot of tooling that is built around filling those particular gaps. How do we get images that have been independently verified so that developers have to spend less time doing this, right? How do we make it easier to have smaller, lighter base images that have fewer assumptions about what they need to run? But this is just one of the problems that led us to say, well, wait a minute. We've kind of seen this sort of heavyweight class with virtual machines. That was sort of supplanted by this, well, not supplanted, augmented by this container runtime system. What if there's sort of like a smaller, faster, even better way to build just the microservice? One that perhaps I don't have to write the boilerplate HTTP code or the JSON encoding or deserializing every time. What if there's a way to do it where I can just write something more like a Lambda, right? That takes a request, does some stuff, returns a response, and my code is only that big instead of that big. And we started looking for different technologies that might fill that particular gap. And the one we landed on was a little bit surprising because it came from the browser. It was called WebAssembly. WebAssembly was started by the Mozilla Foundation. It was one of the rare web projects where they went, as step one, let's build consensus with all the browser makers. So Mozilla, Safari, Chrome, and at the time the actual IE team before they switched over to Edge and then to V8, they all collaborated together to try and scope it out and then define a binary bytecode format and a runtime for that bytecode format that would be essentially language independent. So it had 4 key features in it that made it possible for WebAssembly to play the role it needed to play in the browser. So again, just to step back so I can be fully articulate about another domain I know nothing about. In the browser world, what they really wanted was to be able to run pieces of code that were written in languages other than JavaScript. And again, I'm telling stories, so why not? Inside of Office, so you've got the shift from Office, the desktop app, into Office, the online thing, formerly O365, now Office.com. Excel has some peculiarities dating all the way back to when it was written, and I guess it was Windows 3.1, 3.11, somewhere in there, that have had to be maintained over time. The story goes, and I've been assured that this is a true story, although I don't know all the parties involved. The story goes that there are some libraries that were written for early Excel that did some very low-level, interesting, I think it was date calculation work that were kept in every version of desktop Excel, but written in C. The person who had written the library had long since retired and was gone, and nobody understood what exactly the library did and how exactly it worked. So when it came to replicating everything in JavaScript, people are like, yeah, I'm not touching that one. No, me neither. So a technology like WebAssembly made it possible for them to say, we'll just take that C code, we'll compile it to WebAssembly, we'll expose it to the JavaScript interface, and we don't have to replicate that piece of logic. We'll just use the old 1980s version of this library and keep going happily along. That was kind of one of the problem spaces WebAssembly was designed to solve. Another one was sort of like the Figma cases or the Adobe cases where they need to do very high performance like vector math and things like that, things that are not necessarily JavaScript's strongest point. They could do those in languages like C or C++ or Rust and then compile those to WebAssembly, and then the JavaScript could merely call into those layers. So WebAssembly had to have a couple of key strengths in order to pull this off. The first one is it has to have a really, really good security sandbox, because when we all face it, we trust one application way more than any other application we run, and that's our web browser, right? We just kind of willy-nilly click on URLs, and we assume that the browser will protect us from anything nefarious somebody is trying to do out there. And browser creators, of course, take this responsibility very seriously. So as they built WebAssembly, they said it's got to run in a very strict security sandbox. So strict that you can't use WebAssembly to attack the JavaScript environment in which it's running. So even stricter than the standard sandbox that you use for JavaScript. Has to be cross-platform, has to be cross-architecture. A browser runs on everything from a fridge to your phone and everything in between. And it also has to be really fast. Why does it have to be fast? Research shows that we start to lose our focus on a web page loading when it takes more than 100 milliseconds. For reference, that's about a blink of an eye. So we are tremendously impatient. If a website starts to take longer than a blink of an eye to do something, then we start going, oh, I wonder what's on TV, or our attention begins to drift. Cart abandonment goes up. There's been a ton of research on this. Fascinating to read. So the developers of WebAssembly knew it had to be fast, had to be secure, had to be cross-architecture and cross-platform, and then they took a gigantic gamble and said, if we build it, all these language communities out there that never speak to each other are suddenly going to come together and say, yeah, we're going to support WebAssembly. Rust's going to do it, C's going to do it, Swift's going to do it, JavaScript's going to do it. And that was the big gamble of WebAssembly, that if they built a bytecode format, all these different language communities would implement that format. Amazingly enough, it is largely held true. RedMonk tracks the top 25 languages. 23 of the top 25 languages have WebAssembly implementations. Either compilers or the runtime can compile to WebAssembly. The two outliers are Objective-C, and because RedMonk considers it a programming language, Cascading Style Sheets, CSS. So those are the two languages that don't currently. And I'm told that it should be theoretically possible to compile Objective-C to WebAssembly. I've just never yet met anybody who's done it. So we looked at those strengths of WebAssembly for the browser and went, actually, these are exactly the characteristics you would want in the kind of foundational layer to build microservices that are deploying to the cloud. Has to be a secure sandbox. WebAssembly is more secure than containers because it doesn't even expose the kernel as part of the source that it could attack. So it's somewhere between virtual machines and containers as far as security goes. Cross-platform, cross-architecture is great because now, as we know, we're extending the cloud both from Intel and ARM in the data center all the way out to the edge where we're running on who knows what hardware. I was acutely aware working at Microsoft that fewer and fewer people were running Windows as their server environment inside of Azure, and more of them were running Linux, and we needed to be able to have a runtime that would support both, right? And then, of course, being able to write in your programming language of choice is a boon to any developer, right? So we took WebAssembly and we began trying to build projects that would take WebAssembly out of the browser, put it in the cloud, and make it a great candidate for writing microservice-style architecture. We built a developer tool called Spin. Spin is part of CNCF now. It makes it very easy to go from blinking cursor to a deployed application in a couple of minutes. You can use a wide variety of different programming languages. It builds everything into WebAssembly for you, so you don't necessarily have to become a WebAssembly adept in order to build Spin applications. After we had built a developer tool for it, we said, okay, we need to be able to run this in various places aside from my laptop. And so we built SpinKube, which is an environment to run Spin applications inside of a Kubernetes cluster. There are actually various different runtimes, but SpinKube is also open source and is also part of CNCF, which is why I'm highlighting that one here. So SpinKube basically sets everything up inside of Kubernetes so that I can deploy an application, a WebAssembly application. It'll pull it out of a Docker registry as if it were a Docker image, even though it's actually just a WebAssembly file. And then it'll run it inside of Kubernetes by piping all the way down to the containerd layer, which is what runs containers, and shimming in a Wasm runtime that runs parallel there. So you can run WebAssembly and containers literally side by side. So you can run a pod, if you're familiar with Kubernetes, you can run a pod with two sidecars, one of which is a long-running container and another is a more serverless-style WebAssembly. So SpinKube was a lot of fun to create because it helped us sort of realize some of that vision we were talking about back on that slide when I showed the different sort of types of cloud computing, right? Suddenly we were not trying to go out there and replace containers. Just like containers never replaced virtual machines, WebAssembly is not going to replace containers. But if we can provide different runtimes for different kinds of applications, then we're doing something right. OK, so we just spent a lot of time talking about monoliths and microservices. And you're going, well, wait, didn't you say, is there something in the middle? Well, that's where WebAssembly actually starts to bridge the gap. WebAssembly introduced a new technology that allows us to get some of the benefits that we had back in the monolith days and have them accrue into a more microservice development style. The technology is called the WebAssembly component model because A, it has to be long, and B, we call everything components or nodes, right? But essentially what it is this layer that defines how two different WebAssembly objects can talk to each other. I, as a WebAssembly creator, right, I can write a library and say, hey, I need to import this stuff, and I'm going to export this stuff. And I can do that more or less by contract, right, by saying I need something that satisfies this interface, and I implement this interface. At runtime, when I run that, it runs in its own WebAssembly sandbox. But it can import another WebAssembly sandbox and use that for its upstream dependencies, and then it can attach to another downstream WebAssembly. So effectively, we start to build something similar to like a shared object model, but it's cross-language, cross-platform, language agnostic, all of that kind of stuff. And every component runs in its own security sandbox, which is an entirely new level of security over the typical ways that we do shared libraries, where if you inherit a library and it does something sort of dastardly, there's no way to sort of isolate it. So effectively, just to sidetrack there and give you an idea here, yeah, I think one of these on here is a YAML parser, right? What if I want to use a YAML parser and I want to pass it a string and get back a YAML object, but I don't want to allow that YAML parser to access the file system because I don't know who wrote that YAML parser? The WebAssembly sandbox allows you to say, hey, this thing over here does not get access to a file system whatsoever. If it tries to open a file, it gets a file open error, and the application could deal with it as it will. So suddenly I can start breaking down this application sort of microservice style into different components. And each of these components has its own security boundaries. And I can write each of these components in its own language. But they can actually all live together in the same repository. And I can start writing sort of a single application composed of multiple components. My team can all work on this. We can each have our specialties, and yet we can still kind of pull them all up, run them, and debug them together, right? So the development workflow sort of starts to look like this. We compose a single, code base often if we're building sort of a single unified app. Sometimes we're pulling in, WebAssembly components from elsewhere, but oftentimes we want to build sort of our whole environment together. We can edit it in one project. We can compile it and run it in one runtime. We can test it locally. We can write unit tests that comprehensively test all of the different pieces of this, or functional tests that test the relationship between them. And then here's the kind of cool thing. At deployment time, I can say, hey, I want these components to be sort of spread out in a different topology. I want 8 instances of my front-end component running, but I only want 1 instance of at any given time of my content repository running. And I want my admin interface running over here, but I want it accessible only to people who are internal. And you can start breaking down that one monolithic app into microservices sort of on the fly. So it kind of looks like this. So imagine you've got a Kubernetes cluster, and you're just deploying into one Kubernetes cluster. You can create, and I've got here spin application, which is a CRD type, but effectively it's a deployment, right? I can say, hey, I've got my application where locally it has all these different pieces. When I deploy it, I want it to deploy some of these over here and some of these over here. And then I want to manage these two deployment chunks independently. So one app has now become multiple services. Now, if you can split the application that way within your Kubernetes cluster, can't you just take it one step farther and say, OK, well, actually, I want to deploy the edge or the front end all the way to the edge. I want to deploy one copy of the repository to each of my major regions, but only one copy at each of them. My admin interface never should leave on-prem, right? We'll only deploy it in-house into the internal data center, but it'll still talk to all the other pieces. And so you can start breaking up applications across data centers, across the network. Now, of course, as a developer, you have to be cognizant of the fact that you're going to have latency between these objects now at this point. As soon as you start spreading things out, you'll introduce latency. But you don't necessarily need to do all the hard work of the authentication or things like that, because that can be built right into the deployment stack that you're using. So suddenly, a lot of those security concerns that were causing us as microservice developers a bunch of headaches are going away. I realize that in storytelling, I have now gone way, way, way over time. So let's quickly take a look at one of these. This is what my code base looks like. So I wanted to write a content management system to sort of demo this, because a content management system is relatively ubiquitous and well understood, but also relatively complex, right? So I built this application. Spin.toml is sort of like the main configuration file for any spin app, and you sort of declare all your different components in here, and then you describe each component. So you can see here's a component definition. It defines a bunch of various parameters that I'm not going to necessarily talk about here, but you get the idea, right? I've got a front end, I've got a content repository, I've got a static file server, I've got a navigation tree builder, I've got an admin interface, I've got a token authentication system, I've got a QR code generator, on and on. Each of these is actually a different chunk of code that compiles independently into a WebAssembly binary, but they can all sort of talk to each other. So let's take a very quick look at the QR code generator, right? It's written in Rust. It just basically, you give it a string, it outputs a QR code. You can plant that somewhere. In my CMS, one of the requirements I was trying to show off to a customer was, hey, we could build this thing where when you're showing something on the screen, you can click this QR, you can have this QR code generator on every page so that people can just take a picture of the link and instantly go there and buy that t-shirt, right? So we built this little QR code component out of in Rust for that. But then if we go look at, I don't know, like the front end, this is a traditional TypeScript application that presents the whole front end of my application. All of this is in one repo. And I can build and start all of it and run it all locally. So I'm just going to type spin up. You can see it's actually loading all of those components in. Some of them have publicly exposed routes, others do not. They're just being routed to internally. And then when I go here, I've got my CMS system. When I go log in, which I had already logged in ahead of time so I wouldn't have to type things in, I can see the content management back end of this and go look at my content editor, which apparently I am not running right now. And my menu tree builder and see my asset pipeline and all that kind of stuff. And then I can go back to the front end site and see what it looks like to the end user. So this is a CMS system that was built from somewhere around a dozen different components and then can get deployed all out together. So I'm not going to deploy it to Kubernetes, but I'm going to show you the Kubernetes deployment here so that you can get a look at it. And then we should still have a couple of minutes left for questions. But how many people are familiar with a Kubernetes manifest? I don't want to spend, OK, so I'll skim this pretty quickly. All of these spin app definitions are basically like deployments. And inside of the spec will tell us, hey, when I deploy this app, what am I going to pull in here and what am I going to execute? So the spec for these says, hey, pull in this particular WebAssembly image here. And when you've got this particular image, only activate those components out of this particular image. So only those particular components would come online. So this front end pulls up Luxor front end will pull in just the part that paints the UI, that does some token auth to make sure it can authenticate, and then it's got a caching proxy of the repository so that it doesn't have to upstream for every single content load. So it's very straightforward kind of thing. If we go all the way down to, say, well, the back end is going to run a whole bunch of stuff, because it's really running all the workhorse, the content management system, the asset pipeline, the log notification subsystem, all of that. And then if I go down to the admin is just going to be running sort of an admin backend, a copy of the file server so that we can upload files to that, and a private copy of internal only files that administrators would need to have, like in-flight assets that aren't ready to be published yet. So what we see here is we took one big giant code base that is composed of different components in different languages and built a single application out of them that we could run and test locally. But at deployment time then, we can start to define different ways to deploy these out that include breaking it down into the right grouping of components. So one thing I do want to make clear there is we aren't saying every component has to be its own microservice. All we're saying is that you can choose how to group the components into the right chunk of work that you want running, and then you can manage the right chunk of work. So back to that developer and operations thing, right? What we want to do is say, hey, developer, you build each of these components, each of these microservice-y things the way you want. Hey, operations team, I just inadvertently looked at somebody I know as an operator. Hi, Luke. Hey, operations, hey, Luke, you can just take these components and group them together and say, well, I want to set up the admin to look like this. I want the edge to look like this. I want the content repository to have these components around it. And it's the operational team's concern how it's run and how they manage it from that point on. Okay, that was a lot to take in, but I've got a couple minutes left for questions, I think. 4 minutes. So if you've got any questions, I'm happy to give them a shot. Yep. Yeah, I didn't show the cross-cluster one. What I should have set up ahead of time was one that showed it running on Edge and in Data Center, because that's it can run cross-cluster, can run the version I like to show will run the Edge on Akamai. So we'll run the front end, the QR code generator, and a proxying repository on Akamai's Edge, and then run the rest of the data center, or the rest of it in a data center in, I don't know, AWS or Azure or something like that. And then you just have a TLS connection between the two. And so the proxy cache's point there is to say you really don't want, you want to sort of reduce the amount of traffic across data centers. So as a developer, that's my concern, so I do have to say, okay, well, I'm going to cache some content here. I suppose that's not necessarily the case that I, as a developer, would have to do that, right? Somebody else could say, we're going to run a caching instance here, but it's nice to demonstrate it this way, I think.
Where does that configuration usually live? Is it like in the spin file, or is it in each individual?
Yeah, so that's an excellent question, because it gets back to that developer-operator distinction, right? So the spin.toml file is the developer's view of the world. And the developer says, here are all my components. Here are all the variables that these components need. So when I start up, you can generate what your configuration needs to look like from that. So basically, that's the developer concern file. When it comes to deployment time, then we're talking about SpinKube. That would be a Kubernetes manifest. Or in the Akamai Edge case, we were using, might have been Terraform, to just set some environment variables and then running the application that way. But effectively, the operations team can sort of figure out how they want to do it for the runtime they want to do. SpinKube being the open source runtime that would let you run it inside of Kubernetes. Yep.
Are there good examples of pre-built components that people are running on the edge and things like authentication and other stuff that are out there in the community?
Yeah, so the question was examples of what kinds of components would be run on the edge, and in particular, production use cases. This stuff is new enough that, to my knowledge, nobody's running it in production the way I just showed it, right? However, Spin just builds components by default. And we have definitely seen patterns emerge with how people are doing things, right? Edge workloads are very strongly oriented around optimizing performance, optimizing streaming, caching data that can be cached, and composing things at edge, right? Things that can be last mile composed instead of, whereas in data center stuff tends to be far more heavy compute that is doing some actual generation. Even as I say that, we have noticed just in the last 4 months maybe, a definite shift in interest and temperament, where more and more people are starting to say, I'd like to run edge native, that is no upstream at all. right? Where you say, get everything as close to the edge as possible, run everything out there. CMS being one case that we've seen, AI agents being another case. If you can get a GPU near the edge, then you can do agents in a way that further reduces the amount of traffic, and you can use smaller GPUs that aren't as expensive as the giant class NVIDIA ones. So we've seen a lot of interest in that. Other stuff that tends to drift toward the edge tends to be authentication and authorization. Stuff that drifts toward the data center seems to be data access heavy, one-time large transformations, ETL pipelines, and things like that. This stuff is so new that I don't think we've seen anybody roll into production something systemic, and the stuff that we see people playing around with is still like this level here, where it's a little bit marshmallows and toothpicks. And the component model is not entirely done yet. It's part of a standard called Wasm, and the next version, P3, comes out late this year. So, this is all bleeding edge sort of stuff at this point. I think oh yeah?
Yeah, so I know that Wasm Cloud is also part of the CNCF. What's the differentiator between Spin and Wasm Cloud?
So Wasm Cloud is another CNCF project. The question was difference between Spin and Wasm Cloud. Wasm Cloud is another CNCF project, also uses some of the component model. They use a mesh system, I think, and try and spread it. I don't know a whole lot about it, to be honest. We have effectively, what we have tried to focus on is sort of the serverless style workload with this very pleasant developer experience oriented more toward the microservice pattern. What I'm familiar with from Wasm Cloud from back in the day when I did it, and I have no idea if this is still the case, it was really more oriented towards secure computing and being able to securely load things and verify that they are what they say they are. But again, I have not run Wasm Cloud since 2021, so I'm not really sure. Like them, talk to them frequently, don't know how it works.
Yeah, no worries. It's definitely changed. You should take a look at it.
Okay.
They are using like microservices, serverless.
Okay, yeah. All right, thank you all very much, and I'm standing between you and lunch, so thanks, I appreciate your time.